Okay, sorry this is getting up so late, but it's been a wild weekend. So on Friday, what we talked about was chapter 9, sections 3 and 4, and it was really about inverse matrices. So when you have a matrix, if you can multiply that matrix by something, and you could end up with the identity matrix. This idea is really similar to when you have like a fraction and you multiply it by the reciprocal and you get 1. So like the 32s would simplify, the 5s would simplify, you just get 1. It's a very similar idea. So why do I want this? Because that's a very valid question. And a lot of it comes back to this kind of thing, but this is also a good example. So here we have a system. 10x minus 5y is 35, negative 3x plus 7y is 23. You can model that using this system or this matrix multiplication. And if you look, you'd see like 10x negative 5y is equal to 35. That's where you get this guy. And then this comes from negative 3 times x, 7 times y is equal to 23. And really, what would be super nice is if there was a matrix, so I could multiply this guy and make it basically disappear, right? So like if I could divide by this matrix, but I don't know how to divide, but this is actually a version of dividing, and so that's what we're going to be doing with an inverse, is that if I can get just 1 over here and then multiply by something over here, that's going to be my solution. So that's kind of why I care about this. So here's an example. We're just going to multiply these out, and you will see that we get the identity matrix. So first we'd have 3 times 1 is 3, plus 1 times negative 2 is negative 2. Then we would get 3 times negative 1 is negative 3, plus 1 times 3 is 3. Then we'd have 2 times 1 is 2. 1 times negative 2 is negative 2, so like plus a negative 2, I guess. And then finally, 2 times negative 1 is negative 2, and 1 times 3 is plus 3. And if you simplify this, you're going to get 1, 0, 0, 1. So by multiplying this now hysterical mess, these are inverse matrices, right? Because when I multiply them together, I get 1. Just like if I had 8/3 and I multiplied that by 3/8, I would end up getting 1. Okay, cool. So a question that we might ask ourselves is, how do I get the inverse matrix for this? I've got this example, and one of the ways, and this is decidedly the long way, but it will work, and it would work for you anytime, is you can give yourself some other matrix. So w, x, y, z, and if when you multiply these together you get the identity matrix, you can do that. And this will really give us a system of equations that we could use to get the matrix that we want. Because if we multiply here, so we'd have this by this, and gets us this. So I'd get 8w minus 6y is equal to 1. And then similarly, I could get negative 5w plus 4y is equal to 0. You can solve this system of equations, right? This is just 2 variables, 2 equations, not that bad. You could solve this. We can then also get 2 other from here. If we had 8x minus 6z is equal to 0, and then negative 5x plus 4z is equal to 1. This is another system, and again, it's just 2 equations and 2 variables, so we could solve this. If you go through the work and you actually solve this, you will get this. Oops. W is 2, x is 3, so the matrix that we would end up with getting is, instead of all this up here, get rid of that, is that we would have the matrix 2, 3, 5 halves, and 4. And by all means, pause the video and double check me, but you will end up getting the identity matrix. So if this is L, then this is L inverse. Okay. But that was kind of a lot of work. And in fact, I skipped over a lot of the work. I didn't even solve these for you guys here. I did actually solve them elsewhere. But let's say I want a general solution. And I'm showing you this not because I think that you have to necessarily do this, but here's the idea of how you would get the general solution. You say, okay, I've got this matrix times this matrix. I want this matrix. And you'd go through and you'd do a whole bunch of solving, and you'd drop a bunch of negatives and have to erase a bunch of stuff. And there's more stuff over here. You guys can do this. I think it's like investigation 4, chapter 9.3, something like that. You can do this. And if you do, you will end up finding this, that if you were given the matrix A, B, C, D, that this is what you'd end up with as the inverse matrix. So notice the D and the A just switch places. The B and the C stay where they are, but they become negative, and then we end up multiplying by this scalar 1 over AD minus BC. This is worth knowing, okay? So for any matrix that you need, for example, this one back in the beginning, let's say I want to get the inverse matrix so I can solve this equation. Let's do it. Okay, cool. This right here is going to be my matrix A. You could call it B or whatever you want because I've already got an A up there, I guess. But so I need to find A inverse. So A inverse is going to be equal to 1 over my A value, which in this case is 10, times my D value, which is 7, minus negative 5 times negative 3. And then the actual matrix bit that I'm going to use, I'm going to switch the position of 10 and 7. So it's going to have 7 and a 10. And then I am going to make this a positive 5 and this a positive 3. This guy, when simplified, is 1 over 55. So your final actual matrix that we'd want here that we're solving for would be A inverse is 7 over 55, 1 over 11, 3 over 55, and we'll just leave it as 2 over 55. I can simplify things in my head sometimes. So now what I can do is I can solve this guy. And the way that that would look for me is I would set this up as, we're going to say, A inverse times A times xy, like that, is going to be equal to our matrix here of 35, 23 times A inverse. Final thing will end up looking like this. And I should mention, I've kind of been lax about this thus far. The order, of course, does matter. Because up here, this is a 2 by 1, and this is a 2 by 2. Obviously, because these inner terms don't match, I can't multiply those. So you do actually have to have A inverse over in the front. And then I should also mention that back here, that matrices that have inverses, that these are actually A times A inverse is equal to A inverse times A. Remember, this is not always true of matrices, but if they are actually inverses, they are commutative, and that will work. So when you go through and solve this, you multiply these all together, you're gonna get 1, 0, 0, 1, and I know that because we cooked it to be that way, times xy, which is really just xy, and then on this side you're gonna get 72/11 over 67/11. And I know that because I made Desmos do the work for me. Don't forget, this might be super helpful for you. It might not. Maybe you're just not that excited about it. But desmos.com/matrix has a lot of sweet things that you guys can do with matrix calculators. It'll tell you when you can't do things, etc., etc., and it's free. So go make use of it. So anyways, big idea here is that in order to solve this problem, I was able to use a formula that was fairly simple, which is all the way up here, and is, by the by, in your formula booklet, so there's no reason for you guys to ever have to memorize this. You'll probably get to a point where you know it just because you've done enough of the problems, but you could then use this inverse matrix, multiply it here, and then end up with a solution. Works real slick. Stop. Okay, other thing that we covered on Friday was transformation. So here I have a triangle. That's supposed to look like a triangle. That does not look like a triangle. Jeez, Perkins, why don't you just try to make it super confusing for the kids? Okay, so let me sketch that for you. We got the point 1, 2, we're going to call that point A. We got the point 2, 4. We're going to call that point B, and then we got the point 3, 1. We're going to call that point C. So I have this lovely triangle for you. And this triangle can be made into a matrix where you just take, like, this is point A, X, Y, point B, point C. So here I wrote it out, like, here's the X values, here are the Y values, and you can do that. And a lot of these are in your book, so by all means, or in your formula book is what I mean. But we can do some transformations with this. For example, if I were to multiply this matrix by this one, you'd end up with 0, 2, 2, 0, 4, 0, 1, and then, sorry, I skipped over some of that, but you'd end up with this, and what you end up with, so now we've got the point 2, 1, 2, 1, that's where A went. B went to 4, 2, and C went to 1, 3. Got this new shape, and notice basically all that happened is all the X's and all the Y's just kind of switched places, and in fact it just reflected over this line where X equals Y because the X and the Y switched. And so sometimes when you multiply by various matrices, you'll find that you end up with a couple different things. Very common things, and by all means you should just try these out. If you were to multiply by the matrix like 3, 0, 0, 1, this would multiply all of your X values by 3 and your Y values by nothing, so it would stretch it out this way. If you did like 3, 3, then it would just scale the entire thing up by a power of 3. Check it out. There's also one in there that looks kind of like, cosine of theta, negative sine of theta, sine of theta, cosine of theta. This one will rotate counterclockwise by theta degrees. So those are useful. Those are also in your formula booklet. They are on page 7. Okay, I know that was pretty quick, but this is already a pretty long video. Let me know what questions you have. I will happily help you out with any of this on Tuesday or whatever day.